Close him off. Okay, so again, I'm Bob Bowman, and I'm going to talk about radioactive isotopes and their reverse application. Here's kind of an outline of what I intend to cover over the next 50 minutes or so. This is to start out with an introduction to the concepts of atomic structure, radioactivity, and nuclear reaction. Very top level, and I'm a little, let's say, uncomfortable because I know several of the people who worked here in radioactive materials much longer than I did. I worked 15 years at Mound. They worked longer in a lot of diverse areas, so they probably know more on particular materials than I do. But, you know, let me try to go through and give the overview, so I think I can do that. My area was tritium, so I can cover tritium pretty well, but plutonium or polonium and some of the others, not so much. I'm going to give a kind of outline of what radioactive technology was involved in the Manhattan Project when they developed the atomic bombs, which involved work that was done at the Dayton Project in Dayton, Ohio by Monsanto under contract to the Army in World War II, which led to the forming of the Mound Laboratory in 1948, where we processed a number of radioisotopes over the years for a variety of missions. And then I'm going to have the second half, maybe a little more, on other applications of radioactive elements that are not involved with the space program or military hardware or nuclear power, but all kinds of other things for a variety of different radioactive elements, including some health and medical, which involves some real application and a lot of quackery. You'll be amazed at what radioactive elements are supposed to do for your health. And then a number of the items I'm going to show are actually on exhibit downstairs. A number of them are a new exhibit that we're setting up. So on your way out, you go back to the end of the museum, which is about here. You can see for yourself live a lot of the items that I'm going to cover during the talk. Okay, so let's begin the education. We're going to talk about what's an isotope. And I'm going to take the easiest example that I can think of, i.e. hydrogen. That's the beginning, first element. Get my magic pointer. It consists of, it's called protium, has one proton and one electron. It's number one. It's, proton's a positive charge, electron's a negative charge, and this leads to stable atom. There's also a fundamental particle called a neutron. Neutron means it has no charge. And if you have a proton and a neutron together, you have deuterium, which is called a heavy isotope of hydrogen. There's another isotope that has two neutrons, and that's called tritium. Tritium-3. It's almost no natural abundance, but it's radioactive. That is, it's unstable, and it will decay by emitting a beta particle, which is an electron from the nucleus, in effect changing a neutron to a proton and becoming an isotope of helium-3. So what you have with an isotope is an element, a chemical species like hydrogen, that has three varieties. All three varieties have the same number of protons and an equal number of electrons and some variable number of neutrons. And not all are radioactive. For example, deuterium will last infinite life unless you do something like fuse it together with but tritium is radioactive, so that's what we have. And when we're going to talk about radioactivity, there are three common types of radioactivity that occurs. This is a nucleus. This is a lot bigger. This is, for example, could be uranium. In fact, uranium was the first element that was discovered by accident by Henri Becquerel in France in 1896 to be radioactive. Maybe you heard this story. He had some uranium-containing ore, and we were working with it. He had a photographic plate, and he didn't expose it. And by accident, he exposed it and found out that there was light, that some energy form did the photographic plate, and he identified it as a decay of the nucleus, or decay of the atom, and that was radioactivity. And the type of decay that uranium had is an alpha particle. An alpha particle is basically two protons and two neutrons that's equivalent to the part of a helium, the helium gas, helium atom, the nucleus of that. Another way it can decay is to emit an electron, where I took the example of tritium, where one of the neutrons converts into a proton and throws out an electron from that there, and that's a beta particle. And the third way that you can have radioactive decay is that there are high energy electromagnetic photons. Photons have zero mass, but they're light. And I will give a slide a little further back to kind of explain in context what that is. They're called gamma rays. And the half-life is the time for 50% of the nuclei to transform, that is through decay. And so that's where the half-life comes from. And each isotope that's radioactive has its own characteristic time constant determined by its nuclear structure. Being trained as a chemist, I organize everything with the periodic table. So if you haven't had chemistry for a long time, these are all the known elements that have been identified. And the ones in yellow boxes are the ones that are radioactive. They have all their isotopes are radioactive. None of them are stable. All of those in white boxes have one or more isotope that is stable. Like hydrogen has 2, protons and deuterium, but it has a radioactive one. Now, naturally occurring, there are relatively few of them that were identified early. But we're going to emphasize uranium and plutonium because they were used, and they were the ones that exploited for the first atomic bombs, the first nuclear fission bombs. But just to point these out, they're down here in what's called actinides here. They're called the actinide elements. And there are others. I won't cover all of them because that would be a long time. But we hear that radioactive elements are dangerous and health risks. And it's true, but it really depends on the type of radiation that comes off. You can have a neutron that would come off, usually by a fission process, but you can have an alpha particle, beta particle, or gamma. Now, the energy of that particle runs from what's called kilo electron volts to mega electron, from 1,000 electron volts to 1,000,000 electron volts. So that's the energy of the particle. And its mass. So that determines how much energy is released, and that energy is then dissipated in the environment. The half-life determines how fast those form. And it can be less than a second to over 10 billion years. So some elements are very, very slow, even though they have a lot of energy. And the fourth criteria is concentration, how much of it's there. If not very much, then the radioactivity not so significant. But if you concentrate that radioactive isotope, now you'll have more effect. And in many cases, particularly the elements that have like uranium, plutonium, the actinides, they'll decay and form another radioactive isotope, and it will decay, and so you have a series of those. And there's terminology that was developed in the 20th century to explain, to categorize all of this. And there's activity, and you may hear Curie, which was the old name. It's now called a becquerel. That's the SI is the International Metric Unit, and there's a relationship. The absorbed dose is how much energy is in rads or gray, and then there's the dose equivalent. Dose equivalent is how much energy over and the biological effect of that energy. And the international term is sieverts. And sievert is 100 rem. Rem was for old-timers, people that worked in radioactivity 20, 30, 40 years ago. Rem or rad were the terminology that described the radioactivity level. But nowadays, sieverts, and I'm going to make all the comparisons in sieverts to try to give you an assessment. And what I want to point out is that the background radioactivity level in this part of Ohio is about 0.1 microsieverts per hour. That's what background radiation from very small amounts of uranium in the ground to radon to gamma rays coming in from space, where it's about 0.1 microsieverts per hour. That's how much radiation dose that we have in the back. But it varies depending on what the exact composition is. Now, to kind of give you a range of that, well, what do we expect to see? The radiation dose up to fatal. If you're exposed to 4 or 5 sieverts, there's a 50% chance that you'll be dead within 30 days. That is, the amount of damage to your tissue is such that statistically there. However, if you have a dental x-ray, you'll have about 10 microsieverts. So you can have a whole lot of dental x-rays and not worry about that. So I put example, the U.S. Dose limit is 1 millisievert, 100 times that per individual for the general public. If you're a worker in a radiation area, like at Mound Laboratory or Fernal or somewhere else, then it was 50 millisieverts per hour was an amount of radiation you could be exposed to. And those of us that worked in radioactive areas, we had monitor badges to monitor that and do their urine tests and all kinds of other things to know what exposure you would be. But, and so, for example, if you were in 3 Mile Island, the people that were living within 10 miles of 3 Mile Island got about 80 microsieverts. If you did a CAT scan, and many of us had, I had one a couple years ago, you get something on your 10 to 30 millisieverts. So you get a pretty good dose. But short term, those in the Fukushima accident, the highest dose for the people that were evacuated was in the order of 68 milli. And the highest dose of anyone that was a worker there was 670 millisieverts. Again, it almost a factor of 10 below a lethal dose, statistical lethal dose. But so when you see what level of radioactivity is, sieverts is a big number of what's lethal, and background radiation is a billionth or 100 millionth of that. All right. So now, kind of giving you kind of a quick rundown on what radioactivity is. I'm showing a picture. I don't know if you can see it in the back. These are uranium-238 and 235, the two major isotopes of uranium. 238 is like 99% of all uranium. Less than 1% is 235. The half-life of uranium-238 is 4.5 billion years. That is, when half of a group of uranium atoms have decayed into its first decay product by emitting an alpha particle, it becomes a thorium isotope. Then thorium can emit a beta particle and become something else. And so there's a chain of, so as uranium decays and goes through the different isotopes and different elements, they're called daughter products. They decay, they make something else. I've circled, this is radium. Radium you've probably heard of, and I'm going to explain how it was used a lot. It wasn't discovered until 1898. And there was another one, polonium, that was at Dayton Project and Mound and so forth, that was used. So it's here. And you can get, by the 235, formed the same element, but with a different atomic number, a different isotope was formed. So this chain product here, so when radioactive decay of a heavy element like uranium-238, it goes over a period of time into a whole series. And some of these have very short half-life, days and so forth, but uranium takes 3.5 billion years to do this first step. Well, radioactivity would just be one property. But what was discovered in 1938 and interpreted in 1939 is that if you had a uranium-235 isotope, that's that rare abundance, only less than 1%, and hit it with a neutron, it could be absorbed, excited, and was split into 2 other elements, krypton and barium, throw out 2 or 3 other neutrons that could now hit more uranium-235, split those, and you have what's called a chain reaction. And that chain reaction releases a tremendous amount of energy, mostly in the form of gamma rays, but also these energetic particles. And that was what was discovered and quickly predicted to be a source of new power and energy that could be turned into weapons. And this was discovered just before the onset of World War II. And so that's what kind of was being looked at as a way. And there's a famous letter that was signed by Albert Einstein to Franklin Roosevelt saying that the Germans had discovered this, and that the United States should start looking into it, and that's what happened. At the same time, there were people in the 30s looking at what happened if you could make other elements. And the one that was discovered was plutonium. And plutonium-239 was discovered that it also will, it decays through a chain, makes a uranium isotope. And they made plutonium artificially. It never, almost none existed, but if you take it with a neutron, that neutron will be absorbed. It makes neptunium, another isotope, which emits a beta particle and turns into plutonium-239. And 239 had that rare property, like uranium-235, of being fissile. That it will split when you hit with a neutron and turn into other atoms that emit neutrons. So what that did is there were two isotopes that were discovered in the very early 1940s that could do fission. And what the Manhattan Project did was to develop two types of weapon. The gun assembly, which was based on 235 fission, which was 80% enriched of 235 isotope, and that was a Hiroshima bomb. And this is a schematic where what you had is you had a target of uranium and a bullet, and they were forced together by a chemical explosion. They were subcritical. Critical meant that you had a mass sufficient to be spontaneous and do the chain reaction. And the big challenge was this was less than 1%. And now you're trying to separate a very rare isotope from a more common one, and you had to, with chemistry, that was very challenging. So there was, and that's what the Manhattan Project did. In July, I'm going to give a talk on the Manhattan Project. I'll describe that process a little more, but right now, we'll just say that's what it was used for. Plutonium-239, there wasn't any, but it was decided that it could be put together, and much less plutonium-239 would be fissionable, so you could have, and that became what was the Fat Man bomb, or first the Trinity explosion. And what you had in here, where this is the plutonium that you use a chemical explosion and a spherical compression to get the density high enough so that the fission reaction can occur. One of the problems when they were studying the design and analyzing the material is that plutonium had a tendency to throw out neutrons, and they couldn't, it was going to be difficult to control to initiate the chain reaction. So they needed a source of neutrons in order to fire off under a controlled manner while you're compressing the plutonium to get that fission event. And that was actually identified by Niels Bohr, a future Nobel Prize winner, not for that, but for that thing. And what they found was that the reaction between the isotope polonium-210 with a non-radioactive element, beryllium, that if you the decay particle of polonium-210, alpha particle, and hit the beryllium, it would cause a fusion that would then hit and make those first neutrons. This process of hitting them together absorbs that alpha particle and throws off that neutron, and that starts the reaction. And so both of the Manhattan Project weapons use polonium initiators. Then the polonium had been discovered. Remember, it was one of those decay products of uranium-238. But it was very rare. There was literally, to get a microgram of polonium, you needed a ton of uranium ore. I mean, quite literally is that ratio. But polonium was discovered by the Curies from its property. And in order to do that, they needed that polonium. And this is a schematic of the device called Urchin that the Manhattan Project developed, where you would have polonium, very rare, coated on a beryllium particle that would compress. All the polonium material was separated and processed at the Monsanto Dayton project as part of the Manhattan Project. This was then sent to Los Alamos, assembled into the weapon. This is a simulation, a model of the first atomic bomb, the Trinity bomb, but also the same design of the Fat Man. And on July the 16th, 1945, this was the first nuclear fission explosion reaction detonating of that device. 2 more were done. As I said, the little boy on Hiroshima was a uranium-235 device, and Fat Man on Nagasaki. They ended World War II. Japan then, within a few days, surrendered. The Dayton project continued to process more polonium because the United States continued to build some. In 1946, the Manhattan Project, which has been run by the Army, was transferred to the Civilian Atomic Energy Commission was formed, and Monsanto was working at or oversaw a contract with Clinton Labs in Oak Ridge, Tennessee, and the Dayton operation. And in 1946, the AEC wanted to consolidate all the polonium processing into one site, which was turned out to be the Mound Laboratory built here in Miamisburg. And that's where we came from. And the initial mission was to process the polonium and we're using and fabricating the urchin devices for the first generation of weapon. But over time, Mound existed as an AEC and then DOE laboratory for nearly 50 years, and they developed nuclear components for other devices, both weapons and non-weapons. And non-weapons were the radio thermoelectric generator, RTG, for space program. And the Mound programs evolved. We did Mound people did other isotopes besides the polonium. They started out with radium and actinium. They were looking for alternative. Polonium had a very short half-life, 138 days, so they were looking at ways that they could get neutron sources. They also investigated uranium isotope, protactinium, polonium-239, and they were looking at for power sources. All this work was being done over the years at Mound Laboratory. I'm not trying to give a history of Mound Lab, just pointing out that's what these isotopes were used for. And a polonium prototype was used to make a nuclear battery, a way to make electric power from radioactive decay, from the heat of radioactive decay. And 2 scientists, Ken Jordan and John Burden, came up with the concept, was patented, and in 2013 they were inducted to the Hall of Fame for their invention. Because what this allowed to do that was to make power on systems that were in space, where you could generate power with non-moving, no parts, just heat, and basically it worked. And the best isotope was an isotope of plutonium-238. It didn't not fissible, it won't make an atomic bomb, but it does heat. It had a relatively short half-life, but still on 80 years. And this photograph shows it. It's glowing red from its own heat, from the energy being released from radioactive decay. So it's 24/7 providing heat. It can be converted into electricity, and that powered a whole series of spacecraft. This is the one, the general purpose one. So the Galileo mission that went to Jupiter, the Ulysses that went up out of the plane orbit around the sun, Cassini that went to Saturn, all of those were used this as the power source for the electronics that ran the system, the guidance system, all of that. And they were fabricated here at Mound Laboratory, the actual RTG, in a building that was just behind here, just to the north of here, which doesn't exist anymore, but that's where it was done. And this is kind of an overview of all the missions that the Mound plutonium-238 were done on Apollo, on Viking landers, Voyagers, Earth One, communicate, all these devices. This is a vast story. We've talked about it here before, other lecturers, and I'm sure we'll come back again. If you go down to the museum, if you haven't been there, you can see an overview of some of these missions. The other isotope was Mound Tritium technology, and we were working there. It started in the mid-50s, and the reason is that deuterium and tritium will fuse together to form helium, and with energy and a neutron. And this energy is used to make the fusion bond, the so-called hydrogen bond, as well as the neutron to enhance the yield of fission bond. And what Mound Laboratory had were research, development, and surveillance, where parts would come in. They would mount, people would take parts out of the field, separate the gas, the deuterium and tritium from the helium-3 decay product, and this is actually what they call a pit. They sort of divide the deuterium and tritium in there, and these were set up. So again, these were talked about here. I wanted just to point out those were the isotopes that were processed at Mound. And so what I want to cover now are some of the other applications, the things that weren't part of the AEC or DOE, but were how radioactive isotopes have been used, sometimes even when people didn't know they were radioactive. And so we're going to talk about them. We're going to, uranium was known. There's thorium, which is just a couple elements lighter in the periodic table, americium, polonium, which we've talked about, radium, which I mentioned before, and the tritium isotope of hydrogen. Now, I'm not covering modern medical diagnostics and treatment. Bob Elson, who's here, is going to do that, give a view in May. So come back in a month and you can hear how modern, i.e. Medical technology uses radioisotopes. But for right now, we're going to talk about some of the other uses. As I said a little while ago, another little primer, what's electromagnetic radiation? That's generically light. And the thing is, the frequency or the energy of radiation depends on its wavelength. And so long wavelength are radio waves, and microwaves, you hear, right? Microwave oven, infrared, that heat, that's visible, what we see. Ultraviolet is the real high energy that we can't see. There's X-rays, like X-ray diffraction, X-ray imaging, and then gamma rays. You'll see the wavelength changes from 3 meters or 1,000 meters for radio waves to trillion, 10 to the minus 12 meters for gamma ray. And this is sort of the scale, and this is bottom scale is kind of what that terms to in temperature. So long wavelength is really cold, below 1 degree Kelvin, minus 272. High energy X-ray, they're 10 million degrees Celsius. That's the difference in wavelength. That's the range of energy that you have. It's not linear, it's logarithmic or exponential. And so there's tremendous variation in energy. And the thing is, this high energy will, if it goes into tissues, it will break bonds. It will break chemical bonds because that energy gets dissipated. And so that's why there's there. Now, I took a little chunk of that spectra to bring out again, and that's the ultraviolet and infrared. The longer wavelengths are the infrared, the shorter wavelengths are ultraviolet. Visible, this is what we see from purple to red color that we see here. Ultraviolet light is a little higher energy. It's invisible to us, but you can, it's called black light because it is energy, and a heat lamp is infrared. It's like a heat lamp, so it's lower energy. And as energy goes up, the wavelength decreases. So this is the color spectrum, that very narrow band of electromagnetic radiation that our eyes are sensitive to. And one of the first things that were determined about radioactive material early on was that there's a process called radioluminescence. When light is produced within a material, when an alpha particle at the helium nucleus or a beta particle electron, an alpha particle is what is emitted by radium. And beta particle are tritium and promethium, another element. And when that particle hits an atom or a molecule and excites the electron on that molecule or on that atom to an excited energy state, it will return to equilibrium, but it will, in the process, it'll often lose some energy and come out as a color. And that color is then, that lower energy is then visible to the eye. So what you do is you get electrons from the host material, and the name for it is phosphor. Phosphorescence, you may have heard, like what happens when a lightning bug flashes yellow. That's a phosphorescence phenomenon, but that's a chemical process only, not induced by radioactivity, but only by chemical reaction. But it's the same sort of light. So, the radioluminescence is a means of getting a light source without having to use any external source of power, which means things like signage or clock hands or instrument dial can be read in the dark because it's glowing with that color. And that particular color comes from the chemical composition of the phosphor. And the most common one is a semiconductor called zinc sulfide. It's like a certain type of semiconductor, and it will emit zinc sulfide with some copper atoms in it. It gives kind of a blue-green color. But if you can put copper or manganese, you can get yellow, orange, and there are some others. And this effect was noticed very soon after after the Curies discovered radioactivity, that people started investigating it and found out. And what was found is that radium was really particularly effective. It had about a 1,600-year half-life, that is, half of it would decay in 1,600 years, with alpha particles, and that by 1902, it was being used to paint dials of all kinds of things. This is an example from the 1930s of a clock, and the women are actually painting the numbers on there in the hand. They were done by hand in production line, and this is an example of, this is a clock and this is a pocket watch. I happen to, these are ones that we've done in the museum, shine black light on it because they had faded with time. They're fairly old, and it's not fading because radioactivity fell. It's because the phosphor were damaged gradually by the by the alpha particles, and so they lose their effectiveness in lighting up. But you can see the color. Well, this was a scandal because in order to get the fine point, to put those numbers, the women were told to sharpen the point on a paint with their tongue. And that tongue, then you would swallow a little bit. You were then swallowing radium, which is radioactive. And none of them got sick. There was a lawsuit. But they were still used for decades after that. They changed policy or procedures and no longer were done by the mouth, but they were still radioactive. This is an example of a gyroscope. It would be an instrument. This was an example, and you can't really see the color, but in order to see the meter, this would be, for example, in a ship. You want to see where it is. You want to see it in the dark because you don't have light. This is an example we have. It's actually downstairs in the museum now. And this is my radiation meter. This is 23.3 microsieverts per hour. Remember, background is 0.1. So that's well over 200 times background level of that those gamma particles coming out of that material. And that was made around 1940s. So it's been seen, it doesn't luminesce. And another example that we obtained is a Yarway water level indicator by a company in Pennsylvania in the 40s and 50s. These were in steam engines, steam power plants. And to know what the water level, to see here, this is the meter, see here, so that they would be on a panel back where they were generating steam for power, whether on a ship or in a factory. You can indicate where the water level and control that. Well, this particular instrument, when you put the meter right on top of the dial, is almost 300 microsieverts per hour. Very radioactive material. Because of the radioactivity from radium, and gradually there was an alternative. And the alternative were other isotopes. And the one that was chosen most often is tritium. Tritium is a beta emitter, relatively low energy, that is on the order of less than 18 kiloelectron volts beta particles. A fairly short half-life, so it won't last for about 12 years. And there are no radioactive daughter products. if you recall on those big decay chain I showed, there were lots of other species formed. Most of those are radioactive. Tritium decays into helium-3. It's inert, it doesn't do anything. So it doesn't generate more radiation. And so it's much safer. These are little lights that you can put on keychain. I carry one with me all the time, and it helps me find my keys in the dark. And so, and there's a little bit of tritium gas inside a tube with a phosphorus material around, and you know it's. You don't have to worry about having more children, so it doesn't matter anyway. But the bottom line is, the beta particle can't get out of the glass. They're really very safe, and it works very effectively. And so, you know, you can, and by changing the phosphor, you can get different colors. I like green. Green's very bright, but you can get these colors. We have a couple examples in the museum of different colors. Another device are exit signs. You know, you need an exit sign to go out, and you don't want to run power. You want to run even if the power is gone. The luminescence from that tritium decay gives you that bright light, whether there's power there or not. Half-life is 12 years, so it's good for 20, 25 years, not doing anything, as long as you don't throw rocks at it or anything. So it will, and you can buy these commercially, and so they work. Also, watches. That's the glow. I have a tritium watch too. I like to see in the dark. No, not radium, but it's tritium. Gun sights. You want to see in the dark? You want to, your pistol? You can see the nice bright light point out your target. Very handy. So those are the things that tritium are used. Besides doing tritium in nuclear weapons or looking at fusion energy reactors for power, those are commercial products that you can still buy. Americium is an ionizer, smoke detector. Everybody's house has one. This has an alpha emitter with about 430-year half-life. The alpha particle will ionize the smoke. That gives a little electric signal between electrodes and make the alarm go off. Again, you don't have to have any power. It just runs there. It's 24/7. A microcurie or so, a microgram of those are what you get. So most of them are still there. But there were other similar things, and that was in the 1940s, there were spark plugs that were radioisotopes. What they were using was that polonium-210. Remember I talked about the initiator for the nuclear weapons? You could buy from Firestone a polonium-210 doped alloy that would ionize in a car engine the air before it fired to give you a better burn. That's what it was done, in the spark gap. When it sparked here, it would give you, and this is an ad that 30% fewer revolutions are required to start the motor, make it easier to start your car. They don't sell those anymore, but they did sell them for a long time, for more than a decade. And we have that example down in our exhibit now to show you what were there. Now the polonium only has a 138-day half-life. These were made 50 years ago. There's no polonium left, but the spark plug's still there. So now, I had mentioned very briefly another element is thorium. Thorium is mostly the 232 isotope. Thorium decays, and it decays through radium and other thorium. This is radon. You know, radon is the gas people worry about, but it goes to polonium. But ultimately, it too goes to lead. Lead's the end of the decay. When you get to lead isotope, no more radioactive decay. Now the half-life, this element, not so uncommon. It's like 8 parts per million per year. It's almost like lead. It's 3 times as much as uranium and 4 times as much as tin. So there's a lot of thorium, but it's an alpha particle. That's a decay. But it's 14 billion years. You know, I mean, the thorium that was on Earth was formed at the Big Bang kind of time. Okay, so, but there's a lot of, and it had uses. It had uses not because it was radioactive, but because it could do other things. And people started using it in the 19th century for thorium. They used thorium oxide in what are called gas mantles. You were burning gas. what it does is there's an oxide phase, you form reactant. It won't melt till you get to 6,000 degrees Fahrenheit. You can set a flame, it'll glow really bright white. So if you had a Coleman lantern, or you could, to make that, this is actually an example of a mantle made there. They work very well. They don't use them commercially now, but you can still buy them. I bought that one on the internet a couple of years ago. But they were used for a century. They started from the late 1800s and being available there. This is the background radiation. I put it one right on one inside a piece of paper, another one sitting right on top of it, and you're seeing there 8.5, 11.5 microsieverts per hour. Again, you know, 0.1, so it's almost around 100 times more radioactive than background. But still, 100 times to 1,000 times, you know, before you even get close to being a potential health hazard. But it's still measurable. Now, another property is the thorium oxide. It actually had a very good quality of refractive index. And so when you were making camera lenses, you wanted thin camera lenses that would work. And you needed this high-end cameras starting in around the 1940s would actually be used. And these are Canon, Kodak, Japanese, all kinds of people used them. Now, they were radioactive and it could turn color because of damage from the radioactivity. Modern ones, i.e. in the last decade or two, have used a rare earth element, lanthanum, which is similar. But these are, we have some examples. These are Kodak cameras. This is the reading. We're sitting at 5.5 microsieverts per hour, right, sitting on that top of that lens. And here's a Kodak Sigma camera. These were the cameras that we as consumers bought. These are the good quality, not the fanciest. This is a nice big Kodak lens. It's sitting at 20 microsieverts per hour. So, you know, that's nice big lens of thorium oxide there. So it doesn't make any other color, but it was used for that. And it wasn't used because of radioactivity, it was used because of the other properties. Now, another role that radioactive elements, particularly uranium, had was it could be used to color glass. Because you know, if you don't have any additive to glass, it's colorless, it's clear, it's there. But if you take, these are all, it's silicon dioxide and calcium oxide and sodium in common glass. But if you put iron in, or these are all different elements, gold or manganese, but you can do it with uranium. Uranium has a nice kind of yellow or green color to it. And part of that has to do with the chemistry of uranium. Uranium, besides being radioactive, has a lot of chemistry. It has a lot of different compositions they can form, and they form different colors. So this is uranium with F4, fluorine. This is uranium 306, kind of uranium-02, kind of brown. This is the uranyl, a complex that's kind of bright yellow, and a solution. This is the metal is just a silvery metal. This looks like, you know, aluminum or whatever. And this is uranium trioxide, kind of an orangey color. So that's a piece of uranium metal. But I stole this image from a museum down at White Trail, which Tennessee. I worked there for several years, and they set up a new museum. They had this nice, pretty image, so I borrowed it to illustrate the thing. Well, those colors, people discovered, even as far back as Roman times, that a little uranium gives you a nice color to your glass or to your glaze. And so this is a paper showing all of these materials have uranium, either in the glass or in the enamel, and you get different colors by putting them into the compositions of the glass or the glaze. The glaze would be, you know, the glaze is on a pottery, part that seals it off, keeps the water from getting out, so it allows you not to store fluids in there, store water in there without losing it. Well, turns out that in a particular oxidation state of uranium, it will have a bright green when you hit it with this black light. Okay, we have examples. This is a uranium glass, has there. This is a common, ordinary ultraviolet light, not doing anything. And you see it nice and bright and green. That's the luminescence from the uranyl cation in there. That back. You see, I figure it's relatively safe. They're alpha emitter. It doesn't do much to me. But depending on what else you have, you can have a green uranium glass. If it has a yellow color, the terminology is called Vaseline glass, because that color is almost identical to what old-fashioned Vaseline looked like. Old-fashioned would be, 40 or 50. Modern Vaseline is pretty pale and dull looking, but the Vaseline there, and it would have that color. And it was very popular to put in the glassware, which I'll show you some examples in a minute. I want to jump into a little bit of the science of why is it green? The green has to do with a particular chemical state. This is a schematic, a picture of the uranium atom bonded to two oxygen atoms. This is uranium in the +8 oxidation state with two here, or +6. And so the oxygen are -2, and they're bonded as a species. It sits there as what we call a cation, a positive charged cation. And this species is very stable. It'll take very high temperature. And if you excite it with ultraviolet light, it will emit that green light. This is the wavelength right about here for green light. This is a spectra that was published on the internet to illustrate what it looked like. So that color comes off, that energy that comes off is bright green. And only the uranyl cation give you that color. If you have uranium in a different oxidation state, like the other uranium oxide or so forth, it won't do that. It has to be this species. So here are some examples. They're downstairs. This is normal light. They're green or yellow. This is when you shine ultraviolet light on them, glowing green, all of them. And they are radioactive. Typically, uranium glass runs between 1 and 5 microsieverts per hour. That's the amount. It's not particularly large, but certainly 10 to 50 times above background. There's another use, and that's in porcelain, and this is called what's commonly called fiesta ware. Fiesta ware is dinner, which is a pottery with a uranium glaze in a different oxidation, and it becomes this bright red-orange color. It was started in the 30s. It was very popular. Lots of people had different manufacturers in California, Bauer, so forth, also did that. This was used using natural uranium. Natural uranium has 235 isotope. The fissile material that is used in the first atomic bomb. Well, during the Manhattan Project, you couldn't get uranium, and so the Manhattan Project took away all the supply of uranium. But after, in the late 50s, the company went back and started using depleted uranium. Uranium without the 235 isotope. The 230 isotope is what it was. Again, the chemistry didn't matter. It didn't. The color didn't care whether it was 235 or 238. It gave you the same color. And there's, in the 10 or so years, they made 2 million pieces. This stuff is everywhere. Go to antique stores. Go anyway. You can find it. Here's an example of a couple of pieces. This is a dinner plate. You can, water won't, it's there. This is reading 44.3. This is, not as hot as that, not as radioactive as that radium gauge, but at least an order of magnitude over what the uranium glass would be. This is poppy tree. Poppy tree is a manufacturer with a nice bright red one. This one's almost 59. That's the meter reader, just to show you what it was, but I made it bigger so you could see the scale. So this Chinaware, it's not only red, you can find white and even some blue and so forth that have uranium in. They're radioactive, they don't luminesce, they don't give you pretty colors in ultraviolet light. But nor are they harmful to you unless you start breaking off the pieces and swallowing them. Then it's not so good. But Normally these are very stable surfaces, and there was another application of uranium that I wasn't aware of until a couple of weeks ago when I was doing some research on this for this talk, and it turned out that uranium was also used in photography. As silver was used in the daguerreotype in the mid-19th century, it was discovered that you could use uranium salts. And what you would do is a fellow named Burnett used it in photography with uranyl nitrate. And these are photographs that were printed with the uranium process. And they're not, black and white, there's so much orange there. This was 2 examples. You get, depending on your process, you can get a little different color. But these are uranium type. They're not easy to find. There are currently at least a couple artists in the United States that are making photographs of that, having exhibits of their work where they print with these things. So I'm exploring the possibility to see if we can get one for our museum here to show this use of uranium in photography. Okay, so I've been talking about uses where, practical devices like, china, dishes, spark plugs were used radioactive material. There was also, as I mentioned, that you could use isotopes in medicine. Technetium, for example, is one. Nowadays. But early in the 20th century, radioactivity was a new thing. And people were starting to make all kinds of claims about how great it was and what it would cure. And so I'm going to illustrate those, but first I'm going to say a way it was used, and that was to make uranium dentures. Small amount of uranium in your teeth, and what it would do is, remember the optical properties that would be in porcelain and glass? Well, uranium would do that with dentures to make those look more natural, make more there. And so this is actually a tooth color guide that was patented in 1956. We obtained one of those. It's in the museum. That's what it looks like in normal light. And so if you shine ultraviolet light on these, it glows. I would have loved to find somebody with some uranium teeth and shine a black light in their mouth. I think it'd be very good. I don't know anybody, but hey, if you have some older dentures, and I'm happy to experiment and find out.
Get your shovel, the graveyard's down the street.
There you go, the graveyard down the street. There we go. So, anyway, but here, next is an example which is a radium ore revigorator. This is a jar. It was patented in 1912, and it uses Uranotype, which is uranium ore. Now, they say radium on it, well, there's a little bit of radium in there, but it's basically the uranium ore made into a ceramic. But it's not glazed on the inside, because what you were to do is you were to fill this with water, let it sit overnight, and then drink the water the next day. And continue to do that, and it was good for your health. That the uranium and the radium, and it would prevent lots of illnesses, everything from arthritis, to flatulence, senility, and a whole bunch of other stuff. So the more you drink, the better you'd be. We have one of these examples down in our exhibit. So if you go down the way out, we don't fill water, none of us drink it that I know of. I haven't, but it was sold, and a lot of them were sold. There's another tonic that was actually called Radithor, radioactive water. And this was in the 1920s. And this was radium-226 and 228. Those were 2 different isotopes. At the time, they were still sorting out the radiochemistry of what the elements were, and it had a name of mesothorium, because it actually says radium and mesothorium. It's actually just a different isotope of radium. It has about a microcurie of each of the isotopes in this bottle. It sold for $1.25 a bottle, which was almost $20 in 2019. And they had a list that it would cure up to 150 ailments. I mean, everything was there. And they said, well, it's not a drug. It was there. Well, there was an example of a very famous and wealthy guy named Eben Byers, who was a socialite, that is, playboy, athlete, and still. And he won the U.S. Amateur Golf in 1906, Well, he had a shoulder injury in 27, and his doctor prescribed taking Radithor. And so he took his doctor, and over a 3-year period, he consumed 1,400 bottles of drink. And by 1931, his whole upper jaw and most of it had deteriorated, been removed, and there were holes forming in his skull. He died in 1932. This is a photograph after he took his jaw out, and his brain was accident. He was buried in a lead-lined coffin.
They cured him, they killed him.
Yeah. The government then instituted, the inventor was never prosecuted for this, but it did go off the market. We have an empty bottle down in the exhibit of Radithor. It has some of the claims on it. I checked it, it's not radioactive now, so somebody diluted it a long time ago. Maybe the person drank it, I don't know, but I don't know its history. So that's an example. There are many more where if it had radium in it, it was used. And so I wasn't going to think, lots and lots of times all the examples, but for 40 years or so, and it's still occasionally you'll see somebody, even now, claim that it'll do something. But there's a final example of a radioactive material that, there we go. And that was what was formed in the fireball of the Trinity test in 1945 in Miamisburg, New Mexico. That was in the desert. That's a fireball within like 16 milliseconds of it detonating. What it did, it brought sand from the desert and brought it up into the cloud, and then melted it because it was so hot. And then as it went down, it cooled. And this is the blast area here, and this was covered with this greenish glass that was formed from this melted sand. It had very low level of radioactivity, but it did have some all of this. And in the late 1940s, this became very popular stuff. These are some examples. It was made into jewelry, hair pieces. You could buy it. It was sold as display. We obtained a few small samples, three little samples here. These are counts per minute, so they're not particularly hot, but they are examples. So they are downstairs. It's called Trinity. It's a new element, new material. It was made during the Trinity explosion. Other nuclear explosions that were done in the desert also made stuff, but they're not as well known. But this was the first one. So what I've tried to do, I'm essentially done. I pretty much used my 50 minutes or so, was to give you kind of a highlight of some of the things that radioactivity are like, besides what was done at Mound and was done in DOE in the weapons program. So I thank you for your attention, and I'd be happy to answer any questions that I can. Yes.
There's a fellow on YouTube who did a video making uranium glass. He got some uranyl nitrate and converted it to sodium diuranate, and then mixed it with soda lime glass and fused it. And he observed that during the cooling process of the glass, as it got to maybe 200 C or whatever, it had no fluorescence at all under black light. Yet as it cooled further, it developed that. What causes that change in
I think part of that has to do with the fact that the energy levels are not sufficient for it to emit light in visible. It's probably emitting light, but in other frequencies that doesn't show. And then when it cools down, you'll have those levels now be there because it. So I think that's what's going on. I think I saw the same video, and if you have material and get it too hot, it won't glow as well. But again, he made the glass. It may be that those uranyl cations have other defects near them or something that will short circuit the optical path that we see it for luminescence. Yes.
All of those decay chains that you showed, I think they were in the actinides. Do all of those end up lead?
All of these do.
Okay.
I think there may be a couple others. I'm really not a nuclear chemist, so like I said, I've always been a little nervous.
All the ones you're familiar with.
All the ones I'm familiar with, and the common ones that have been used end up going to lead. So uranium goes to the lead.
We all knew about those, that radium and the watch dials, but it never occurred to me, do you know what phosphor they would have used back then?
Usually, it was a semiconductor, zinc sulfide, what they've been using most, because I think it was known to be compounds. And they would literally mix a little bit of radium salt with, a very little bit, with the semiconductor salt, usually doped with something to give them.
And some oil binder.
Oil binder, usually with a binder, and then that would go to make it kind of water soluble so they could paint it.
Right.
And so that's what they would do.
Thank you.
So.
Wow. If you're talking about the phosphors, the zinc sulfide with different additives
Yes.
give you different colors.
Right.
And the colors come from impurity sites within the crystal structure of zinc sulfide.
Right. Yeah, zinc sulfide has a too wide a band gap.
Yeah.
Yeah. So what you have are states either above the valence band or below the conduction band that now fall with an energy that corresponds to a visible light.
Visible light, yeah.
And so that's how you can change the color. Now, for example, with the tritium light, it's the same. Tritium uses the tritium lights use the same principle. They use the same semiconductor for the light. They just use a beta particle from tritium to excite it rather than an alpha particle from radium.
What are the makers of your key lights and sights and exit signs and so on? Where do they go to buy tritium?
Well, they get it on
eBay. On eBay.
Canadian. You don't get it on eBay, but a lot of them are made in Switzerland. Switzerland gets it, and of course you can get tritium small amounts from different. I think Mound was going to try to sell tritium lights at one time, or at least you were working.
We worked on some of them.
Yeah.
But the company in Switzerland is MB Microtech.
Yeah.
I think they're still in
Yes.
existence. And like you say, you can buy tritium from Canada for non-nuclear applications.
Yep.
And that's where most of it comes.
Most of it comes from Canada, to my knowledge. Now, if the Chinese are making it, they probably make their own because they have their own reactors. They're not so good at doing international trading, I think. But again,
I should say for non-weapons applications.
non-weapons application. It is non-weapons application.
Yeah, because most of our medical isotopes from those 2 reactors in Canada.
Yeah, and some Oak Ridge has a reactor that sells some too, because you can do that. So, anyway, I do thank you for your attention. Remember, on the next month, on the 25th of March, Dick Church is going to be here talking about what happened to his experience with the transformation of Mound from DOE Production and Research Center to a free enterprise company and business park that involved. And then we'll have Andy Askin's going to talk, and then Bob Elson is going to talk about radioisotopes in medicine. So he has a couple of months to tell you how things are, other ways to use it that are still acceptable. All right, thank you everyone, and have a safe drive back home.